For 65 years, we aimed telescopes at stars, listened for radio signals, and built a checklist designed to find one thing: another Earth. But the most common planet in the galaxy is nothing like Earth, and we ignored it for decades. What if the entire search for alien life has been asking the wrong question? You are about to discover why a $10 billion telescope went silent at its most controversial moment, why the molecule we trusted most to detect life turned up on a lifeless comet, and why the framework guiding the search was built on a sample size of 1. If that pulls you in, hit subscribe. We begin now. On the night of April 8th, 1960, a 30-year-old astronomer named Frank Drake sat at the controls of a radio telescope in Green Bank, West Virginia, and pointed it at a star. The telescope was 85 feet across. The star, Tau Ceti, sat 11.5 light-years away. Drake was not conducting an astronomy experiment. He was listening for a conversation. He called the project Ozma, after the queen of a faraway land in a children's book, and the choice of name was less whimsical than it seemed. Drake genuinely believed he might hear something. He had chosen the frequency deliberately, 1420 MHz, the resonant frequency at which hydrogen atoms emit energy when their electrons flip spin states. Hydrogen is the most common element in the universe. Any civilization that understood basic physics, Drake reasoned, would recognize it as the universal radio channel, the one frequency all intelligent beings would know to monitor. He swept across Tau Ceti, then shifted to Epsilon Eridani, another nearby star. He ran the search for 150 hours across several months. He heard nothing except a brief false alarm from a military aircraft passing overhead. What Drake had launched was the search for extraterrestrial intelligence, and the 150 hours he spent that spring established a template that would govern the field for the next 65 years. The following year, he convened a small gathering at Green Bank to formalize the logic behind the search. About 12 people came, including Philip Morrison, Carl Sagan, and a dolphin researcher named John Lilly. To organize the conversation, Drake wrote 7 variables on a chalkboard and multiplied them together: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, and 4 more factors covering the emergence of life, intelligence, communicating civilizations, and how long they survive. The result, in principle, was the number of detectable civilizations in the galaxy at any given moment. Drake himself called it a way of organizing ignorance. He never intended it as a predictive formula. The problem was that the first 3 variables eventually became measurable, while the last 4 remained completely unknown. Every estimate of them was based on a sample size of 1. There is one planet we know with life. There is one civilization we know achieved technology. There is one species we know started broadcasting radio signals. Every estimate of how often those things happen elsewhere was essentially a guess about outcomes we have seen exactly once. Scientists plugging numbers into the Drake equation were not doing astronomy, they were doing autobiography. The deeper failure was structural, and it took decades to name clearly. The entire architecture of the search assumed that extraterrestrial civilizations worth detecting would resemble mid-20th century Earth. They would broadcast on radio frequencies, they would use the hydrogen line, they would transmit signals into space in ways detectable from other stars. A civilization that had moved beyond radio a century earlier, as our own civilization is now doing as fiber optics and satellite technology increasingly replace radio broadcasting, would be completely invisible to every telescope Drake's successors built. In 2015, the Russian entrepreneur Yuri Milner committed $100 million over 10 years through the Breakthrough Listen initiative, the largest private investment in the history of the search. The instruments grew more powerful, the sky coverage expanded dramatically, the underlying assumption never changed. 65 years after Project Ozma, researchers at Robert Stern's group at the University of Texas at Dallas published a revised estimate of how often intelligent life arises in the universe. Their April 2024 analysis incorporated plate tectonics as a prerequisite, based on evidence that complex animal life on Earth did not appear until after the modern episode of plate tectonics began roughly 600 million years ago. The revised probability dropped the optimistic estimate of how often intelligence emerges by orders of magnitude. The silence, it turns out, was not the most interesting thing about the search. The most interesting thing was what the search had always been designed to hear. James Casting was not trying to narrow the search for life, he was trying to make it tractable. In 1993, the Pennsylvania State University planetary scientist published a paper in the journal Icarus that formalized what became known as the circumstellar habitable zone, a band of distances from a star where a planet could maintain liquid water on its surface. Too close, and the water boils away. Too far, and it freezes. Inside the zone, the thinking went, conditions resembled Earth closely enough to support organisms. The paper became one of the most cited in astrobiology, and the concept it introduced drove telescope designs, mission priorities, and the public imagination for 3 decades. Scientists called it the Goldilocks zone. The name stuck because it perfectly captured the appeal, a special place, neither too hot nor too cold, where life got everything just right. There was a problem embedded in the framework that took an embarrassingly long time to surface fully. Mars sits inside the habitable zone of our star, so does Venus. Mars is a freeze-dried desert where average temperatures hover around -80 degrees Fahrenheit, where the atmosphere is less than 1% as dense as Earth's, where liquid water vanished from the surface billions of years ago. Venus is covered by clouds of sulfuric acid, has surface temperatures that exceed 860 degrees Fahrenheit, and exerts atmospheric pressure 90 times greater than Earth's at sea level. The habitable zone had predicted 2 habitable planets and produced 2 of the most hostile environments in the solar system. The framework had been built around the wrong premise, and the proof of that wrong premise had arrived 16 years before Casting published his paper. In 1977, marine geologists, surveying the floor of the Pacific Ocean near the Galapagos Islands, descended into total darkness to discover something that should not have been there. At depths of 8,000 feet, where no sunlight had ever reached, where pressure would crush an unprotected human body, where temperatures near hydrothermal vents climbed above 700 degrees Fahrenheit, there were entire ecosystems. Giant tube worms nearly 8 feet long, clams, crabs, fish. Entire communities of organisms running entirely on chemical energy rather than light, built around bacteria that converted hydrogen sulfide into food through a process called chemosynthesis. Life had been thriving in the exact conditions the habitable zone framework assumed were impossible. The discovery of hydrothermal vent ecosystems in 1977 should have prompted an immediate revision to every assumption scientists were making about where life could exist. Instead, the habitable zone framework, published in 1993, treated surface conditions and sunlight as prerequisites. It continued to drive research priorities for another 30 years. Europa, the moon of Jupiter, sits nearly 5 times as far from our star as Earth, far outside any habitable zone, beneath an ice shell up to 30 miles thick. Beneath that ice shell sits a liquid ocean 60 to 100 miles deep, more liquid water than all of Earth's oceans combined, in direct contact with a rocky seafloor that may host hydrothermal activity. Enceladus, a moon of Saturn, was shooting active geysers of liquid water into space. Both worlds were technically irrelevant under the framework that guided the search. The checklist had been written without asking whether the universe had been reading the same textbooks. When the Kepler Space Telescope began returning data in 2009, astronomers expected to map the distribution of planets across the galaxy. They got that. They also got something they had not planned for, an entire category of planet that nobody had seen before and that no existing theory explained well. Planets between roughly 1.5 and 3.5 times Earth's radius turned up everywhere. Around nearly every star Kepler examined carefully, in orbital periods ranging from a few days to a few months. In architectures that bore no resemblance to our solar system's orderly arrangement. Astronomer Eric Pettigura and colleagues at the University of California, Berkeley confirmed in 2013 that these worlds, which researchers eventually called sub-Neptunes, orbit more than half of all stars similar to our own. They are, by straightforward measurement, the most common type of planet in the galaxy. Our solar system has none of them. Between Earth, roughly 8,000 miles in diameter, and Neptune, nearly 31,000 miles across, there is a gap in planet sizes that simply does not exist in most other systems. That gap is not representative of the universe. It is a peculiarity of our neighborhood, possibly a consequence of specific events in our solar system's early formation, possibly a gravitational coincidence that does not recur often elsewhere. For decades, that gap had invisibly defined what scientists considered a planet worth thinking about. The planets they understood were rocky worlds with thin atmospheres or gas giants with thick ones. Sub-Neptunes fell between those categories in a way that made them scientifically awkward and, under the habitable zone framework, effectively irrelevant. The decision to set them aside had a precise logic. The habitable zone framework was built around rocky planets with surface water and thin atmospheres. A world 2.5 times Earth's radius could have a thick hydrogen atmosphere wrapped around a global ocean. It could be a small gas giant with no surface at all. Without a way to distinguish between those possibilities, and without the instruments to study their atmospheres in detail, researchers filed them in a mental drawer labeled as uninteresting and moved on. They were scenery, not candidates. Dirk Schulze-Markuch at the Technical University of Berlin and Louis Irwin at the University of Texas at El Paso had been arguing for years that the field's focus on Earth-like conditions was, in their words, too restrictive. The habitable zone framework, they wrote, was biased by terracentric assumptions. The assumption that because Earth produced life, Earth-like conditions were what mattered. What the Kepler data was actually showing was that the most studied planet type in our solar system, the rocky world with a thin atmosphere, was the outlier. The vast majority of planets orbiting other stars were something else entirely. The habitable zone framework, designed to find Earth-like planets, had been built around the rare exception, while the common rule sat unexamined. Spending decades searching for life on the rarest kind of planet in the most difficult atmospheres to study, while setting aside the most common and most accessible type, required some justification the field had never fully provided. In September 2019, 2 independent research groups published papers within days of each other, reporting the same finding: water vapor in the atmosphere of a planet called K2-18b. One group was led by Bjorn Benneker at the University of Montreal. The other was led by Angelos Tsiaras at University College London. They had both analysed observations from the Hubble Space Telescope, and both had found the same chemical fingerprint in the light filtering through the planet's atmosphere during its transit across its star. The detection itself was not especially controversial. The controversy was about what it meant, because K2-18b was not the kind of world where anyone had seriously expected to find anything interesting. The planet sits 124 light-years away in the constellation Leo. It orbits a dim red star, a type known as an M-dwarf, once every 32.5 days. It has a radius 2.5 times Earth's and a mass 8.5 times Earth's. Those numbers placed it squarely in the sub-Neptune category, the category that had been treated as scenery for the previous decade. It had been discovered by the Kepler telescope in 2015 and had since attracted almost no attention. Now, it had confirmed water vapor in its atmosphere, and it sat inside what astronomers calculate as the habitable zone of its star, which meant the question of what to make of it became unavoidable. The question proved genuinely difficult to answer. A planet of K2-18b's mass and radius could be many things. It could have a rocky core wrapped in a deep hydrogen atmosphere above a liquid water ocean. It could be a water world without any rocky core at all. It could be a small gas body whose interior, under enormous pressure, transitions smoothly between gas and liquid without a distinct surface. The Hubble data confirmed water vapor existed. It said almost nothing about what kind of world was producing it. Niku Madhusudan at the University of Cambridge had been thinking about sub-Neptunes for years before the water detection. In August 2021, his team published a paper in the Astrophysical Journal, introducing a formal new category, the Hycean world, a name combining the words hydrogen and ocean. His argument was that a water-rich sub-Neptune with a hydrogen atmosphere could maintain liquid water at its surface across a far wider range of distances from its star than any rocky planet, because the hydrogen acted as an extreme greenhouse gas-trapping heat that Earth's thin nitrogen atmosphere could not. Hycean worlds also offered a practical advantage that rocky planets could never match. Their thick, low-density atmospheres produced signals in transit spectroscopy many times stronger than the wispy envelopes around smaller worlds. The implications for the search were immediate and somewhat unsettling. If Hycean worlds were habitable, and if they were the most common type of planet in the galaxy, and if their atmospheres were far more readable than anything smaller, then the entire previous strategy of searching for Earth-sized rocky worlds in thin habitable zones had been targeting the worst possible candidates. The instruments built to study Earth analogues could barely read their atmospheres at all, requiring hundreds of hours of observation time for a single planet. A Hycean world offered the same information in a fraction of the time. Madhusudan said it directly. Hycean planets opened a new avenue in the search, offering a substantially better chance of finding biosignature molecules. The planet that had sat ignored since 2015 was now the most strategically important object in the field, both scientifically compelling and, critically, actually measurable, with instruments that already existed. Dimethyl sulfide does not smell pleasant. It is the compound responsible for the odor of low-tide mudflats, of rotting seaweed, of the sea itself on a heavy afternoon. Bacteria in ocean surface waters produce it in enormous quantities as a byproduct of processing a substance called dimethyl sulfoniopropanate, which marine algae synthesize to regulate their cell membranes. When those algae die and their cells break down, bacteria metabolize the compound and release dimethyl sulfide into the atmosphere. It rises into the clouds, where it contributes to rainfall over the oceans. It is, in ways that took decades to fully appreciate, a product of planetary-scale biological activity. The oceans of Earth exhale it continuously. For astrobiologists searching for chemical evidence of life on other worlds, dimethyl sulfide occupied a privileged position. The logic was compelling. On Earth, significant production of this molecule requires living organisms. Scientists had searched repeatedly for abiotic pathways that could produce it in meaningful quantities without biology, and they had consistently come up short. The molecule was not impossible to form through chemistry alone, but the amounts chemistry could generate were negligible compared to what living ecosystems produced. When telescopes began achieving the sensitivity to analyze the atmospheric chemistry of planets orbiting other stars, dimethyl sulfide became what researchers called a biosignature gas, a compound whose presence in an alien atmosphere would be difficult to explain without invoking life. Sarah Seeger at the Massachusetts Institute of Technology, whose work on biosignature gases shaped much of how the field thinks about atmospheric detection, included dimethyl sulfide in her systematic surveys of chemical markers worth searching for. The molecule had what biosignature researchers value most: a strong biological source and a weak abiotic background. A planet producing it in large quantities would be hard to explain with chemistry alone. Seeger's group catalogued more than 14,000 molecules as potential biosignature candidates, but dimethyl sulfide held a special status among them. It was not just theoretically promising, it had been tested against alternative explanations and survived. The decades of failed searches for non-biological production had done something that relatively few biosignature candidates could claim. They had actively strengthened the molecule's credentials through the failure of every attempt to produce it without life. The certainty that had accumulated around this molecule began to unravel in 2023. Nora Henney and colleagues at the University of Bern published findings from the Rosetta mission, which had spent years orbiting Comet 67P, Churyumov-Gerasimenko, a frozen, irregular body tumbling through the void between Jupiter and the asteroid belt. The comet had no ocean. It had no atmosphere in any meaningful sense. It was a chunk of ice and dust with no possibility of biology by any definition the field had ever used. The Rosetta instruments detected dimethyl sulfide in the vapor rising off the comet's surface as the warmth of the distant star sublimated its outer layers. The same year, a separate research team found the molecule drifting in interstellar molecular clouds, in regions between the stars where temperatures approach absolute zero and no organized chemistry of any complexity could sustain itself. The molecule that supposedly required life had been found in two places where life was impossible, and the foundation of the field's most trusted detection method had quietly cracked. The James Webb Space Telescope costs approximately $10 billion. Its gold-plated mirror spans 21 feet across, and it operates at temperatures near absolute zero, shielded from the warmth of the star behind a sunshield the size of a tennis court, orbiting a gravitationally stable 0.1 million miles from Earth. It was conceived in the early 1990s, approved in 1996, delayed for more than a decade by cost overruns and technical setbacks, and finally launched on Christmas Day 2021. Its design had been optimized from the beginning for the infrared wavelengths where molecular fingerprints in distant atmospheres are most readable. It was, in an important sense, the instrument the field had been waiting for since the habitable zone framework was first written. In the summer of 2023, Webb pointed its instruments at K2-18b during one of the planet's transits across its star. When a planet crosses its star from our line of sight, a small fraction of the star's light filters through the planet's outer atmosphere. The different molecules in that atmosphere absorb light at specific wavelengths, leaving gaps in the spectrum that function as a chemical fingerprint. For years, the atmospheres of sub-Neptunes had been too faint, too poorly characterized, too uncertain in their basic structure to read clearly. Webb's sensitivity changed that. The data that came back from K2-18b contained detections of carbon dioxide and methane together, the first confirmed carbon-bearing molecules in the atmosphere of any planet orbiting inside a habitable zone. For reasons related to atmospheric chemistry, the simultaneous presence of both gases is itself unusual and might under some circumstances indicate biological activity mediating the carbon cycle. Those detections generated scientific papers and genuine excitement. Then the Cambridge team found something more in the longer wavelength infrared data, a feature they attributed to dimethyl sulfide. It was tentative, sitting at roughly 1 standard deviation of confidence, and they said so. A press release from Cambridge University in September 2023 used the phrase, "possible evidence of life." The sentence traveled around the world in hours. The coverage was extraordinary and immediate. Media across every major platform treated the phrase as a near confirmation. Interviews were scheduled. Editorial boards weighed in. The Cambridge University press office had used careful, conditional language, but the headline writers had largely stripped it out. NASA said nothing. The agency whose $10 billion telescope had produced the measurement issued no statement, no press release, and no comment of any kind. Every prior Webb discovery of comparable significance had come packaged in an official release with context, imagery, and institutional framing. The first detection of an exoplanet atmosphere, the first light images, the first carbon dioxide in an exoplanetary spectrum, each had generated immediate, enthusiastic communication from the agency. This time the agency was silent, while the university that had processed the data controlled all public messaging. Inside that silence was a judgment, and the judgment was that the evidence being announced did not yet meet the bar the agency applied before speaking publicly. What that gap between Cambridge's certainty and NASA's silence revealed about the state of the field would take 18 months of further analysis to fully expose. On the morning of April 3, 2025, the Cambridge team published a new paper in the astrophysical journal Letters. Madhusudan, along with Mons Holmberg of the Space Telescope Science Institute in Baltimore and other collaborators, had analyzed new observations from Webb's MIRI instrument, data collected specifically to follow up on the 2023 tentative finding. The new result was stronger. The paper reported detection of dimethyl sulfide and possibly dimethyl disulfide at 3 sigma statistical confidence, meaning the probability of the signal being random noise was approximately 0.3%. In particle physics, 5 sigma is the threshold for claiming discovery, but 3 sigma is broadly regarded as strong enough to warrant serious attention. The concentrations implied were extraordinary, more than 10 parts per million, potentially thousands of times higher than the levels Earth's oceans produce. Jake Taylor at the University of Oxford read the paper and ran the data himself. His counter-analysis, posted to the public preprint server within days of the Cambridge publication, reached a different conclusion. When he applied what he described as an agnostic retrieval approach, making fewer assumptions about what molecules should be present before looking for them, the feature the Cambridge team attributed to dimethyl sulfide disappeared. The data, Taylor concluded, was consistent with a flat line, a featureless spectrum containing no meaningful chemical information at all. Laura Kreidberg at the Max Planck Institute for Astronomy in Heidelberg articulated the core of the problem in terms the broader scientific community found difficult to dismiss. A robust detection, she said, should survive changes in underlying assumptions. If the signal appears only when you assume it should be there and vanishes when you approach the data without that assumption, the signal is not robust. Kevin Stevenson at Johns Hopkins Applied Physics Laboratory was more direct. The overwhelming consensus among the researchers he had spoken to was that the enthusiasm in the Cambridge announcement exceeded the strength of the evidence by a considerable margin. The NASA-led counter-analysis found that Webb's MIRI instrument in the relevant wavelength range was highly susceptible to unresolved instrumental systematics, producing noise patterns capable of mimicking molecular absorption features. Of 8 alternative analysis approaches applied to the same data, 7 found no dimethyl sulfide signal. 87.5% of all independent analyses, in other words, saw nothing. Madhusudan's team responded that their atmospheric model was more physically realistic, incorporating the actual behavior of hydrogen-dominated atmospheres, and that this realism was what produced the higher significance. The response was not unreasonable on its face. Different retrieval models genuinely produce different results, and a model that better represents the physics of the atmosphere should in principle be more accurate. The dispute had become circular in a way that is common at the frontier of detection science. Each side was contesting not just the conclusion, but the framework by which the conclusion should be evaluated. Kevin Stevenson put the practical problem plainly. Without agreement on what constitutes an adequate analysis, the same data can be published twice, reaching opposite conclusions, both passing peer review, leaving the scientific community with no mechanism to decide which is correct, except to collect more data. 16 to 24 additional hours of Webb observation could, in principle, push the detection toward 5 sigma if the signal were real, providing enough statistical weight to make the methodology dispute secondary. As of early 2026, those observations had not been scheduled to completion, and the two camps remained at an impasse that debate alone could not resolve. After 8 years of continuous study, researchers still cannot say with certainty what K2-18b actually is. This is not a gap that better instruments will soon close. It reflects a fundamental difficulty in characterizing a class of world that has no nearby example to examine, no surface missions to ground truth, no analog in our solar system against which to calibrate expectations. K2-18b is too massive to be a rocky planet. With the kind of thin secondary atmosphere Earth developed through outgassing, and it is not massive enough to have accumulated a deep hydrogen envelope the way a true gas giant does. It occupies a middle category that planetary science built none of its core intuitions around. If Madhusudan's Hessian interpretation is correct, K2-18b has a planet-wide ocean, perhaps hundreds of miles deep, covered by a hydrogen-rich atmosphere. The ocean surface sits under pressures and temperatures that, depending on exact atmospheric composition, might remain within ranges where Earth-like biochemistry could operate. Microorganisms producing dimethyl sulfide at industrial scale would float through that ocean, surrounded by hydrogen above and liquid water below, having evolved under conditions no organism on Earth has ever experienced. The planet's host star, a red dwarf less than 1/3 the mass of our own, radiates a spectrum heavily weighted toward infrared wavelengths, quite different from what drove the photosynthesis that shapes Earth's atmospheric chemistry. Any biology in that ocean could not rely on the same light-harvesting mechanisms that terrestrial life uses. What energy source would drive metabolism there, and what the metabolic waste products might be, remains entirely a matter of speculation. If the Hessian interpretation is wrong, K2-18b may have no surface in any meaningful sense. Beneath its atmosphere, pressure and temperature would increase continuously through supercritical fluid phases into a mantle of high-pressure ice, and finally into a rocky core at pressures thousands of times those at Earth's ocean floor. There would be no interface between liquid and atmosphere, no concentration zone where chemistry could accumulate and react in the way most origin of life researchers believe necessary for life to start. The two descriptions are not minor variations on a theme. They are fundamentally different planets, with different histories, different internal structures, and different answers to whether life could exist. One has a potential biosphere. The other has nothing recognizable as a surface. The uncertainty between them is not merely semantic, and the reason it cannot be resolved yet comes down to a basic limitation of what transit spectroscopy, even with the most sensitive instrument ever launched, can actually tell us. It reads the edge of an atmosphere during a few hours of transit. It says nothing about what lies below. Understanding K2-18b in the way planetary scientists understand Mars, through surface missions, seismic data, and direct sampling, is not something that will happen within any foreseeable mission timeline. After 8 years of observations and a global media event, researchers cannot say which of these two fundamentally different worlds they are studying. That is the normal state of knowledge about sub-Neptunes, the most common planets in the galaxy, and it was the normal state of knowledge long before K2-18b became famous. For approximately 30 years, dimethyl sulfide held a special status in the biosignature literature. Researchers catalogued hundreds of potential marker gases, but most had known abiotic sources that weakened their value. Oxygen can be produced by photochemical splitting of water. Methane seeps from volcanic activity. Nitrous oxide forms through lightning. Even phosphine has been detected emerging from Saturn's gas envelope under high-temperature, high-pressure conditions with no biology involved. Dimethyl sulfide seemed genuinely different. Research teams working systematically through the chemistry of planetary surfaces, of cometary material, of interstellar ice analogues under laboratory conditions, kept failing to generate it in significant quantities through purely chemical means. The community concluded, after sustained effort, that meaningful production required living marine ecosystems. The decades of failed abiotic searches were the evidence. They were enough to build a scientific consensus on. The consensus was built on absence. No one had proven that abiotic dimethyl sulfide was impossible. They had simply looked in the obvious places and found nothing. That is a different kind of evidence, and it is weaker than it looks, because absence of evidence in a limited search is only as reliable as the completeness of that search. The Rosetta mission of the European Space Agency had spent 12 years in transit to Comet 67P Churyumov-Gerasimenko before arriving in 2014 and flying alongside it for 2 years. Data from the mission was still being processed years after the spacecraft's controlled impact on the comet's surface in 2016. In 2023, Nora Henney and colleagues at the University of Bern published an analysis confirming dimethyl sulfide in the vapor the comet released as warmth sublimated its outer layers. Comet 67P is a frozen aggregate of dust and ice roughly 2.5 miles across, tumbling between Jupiter and the asteroid belt, with no atmosphere, no ocean, and no chemistry capable of supporting life by any existing definition. It contained the molecule that supposedly required life to exist. That same year, Marta Sanznovo and colleagues reported detections of dimethyl sulfide in interstellar molecular clouds at temperatures within a few degrees of absolute zero. Molecular clouds are not unusual environments. They are the enormous masses of gas and dust scattered across every galaxy from which all new stars and planets eventually form. Finding dimethyl sulfide drifting through them, assembled through reactions driven by cosmic radiation and cold chemistry in a region where no life could conceivably exist, was a direct demonstration that the molecule formed without biology in the conditions that precede planet formation itself. The following year, laboratory experiments under simulated exoplanetary conditions reproduced dimethyl sulfide through purely inorganic chemical reactions. Shangmin Tsai at the University of California, Riverside published atmospheric models showing that even without any biology at all, a hydrogen-rich atmosphere over a warm ocean could accumulate the molecule at concentrations approaching what the Cambridge team was claiming to detect on K2-18b. The abiotic pathway could, in principle, explain the entire signal the Cambridge team was attributing to life. Sara Seeger acknowledged the cumulative weight of this evidence directly. Dimethyl sulfide, she said, could no longer be considered a robust biosignature. The molecule the field had spent 30 years trusting most had, in the span of roughly 2 years, become just another ambiguous chemical whose presence proved nothing about the presence or absence of living organisms. In August 1996, President Bill Clinton stood at a podium outside the White House and described evidence that primitive life may have existed on Mars more than 3.5 billion years ago. Behind him was a photograph of the Allen Hills meteorite 84001, a chunk of Martian rock that had landed in Antarctica after an asteroid impact ejected it from Mars billions of years ago. Inside the rock, researchers from NASA's Johnson Space Center reported microscopic structures resembling fossilized bacteria and chemical compounds associated with biological activity. The announcement was immediate, presidential, and heard by hundreds of millions of people. By the early 2000s, the scientific consensus had shifted decisively against the biological interpretation. The microscopic structures were smaller than the minimum size a bacterium requires to contain functional cellular machinery. The magnetite crystals, initially cited as potentially biological, formed readily through abiotic mineral reactions under conditions matching the meteorite's known history. The paper had passed peer review. It had received presidential endorsement. The correction arrived through journal correspondence and conference presentations, reaching a fraction of the audience that the original announcement had. In September 2020, Jane Greaves at Cardiff University announced the detection of phosphine in Venus's atmosphere at 20 parts per billion, a level she and colleagues argued was impossible to produce without microbial life in the planet's temperate cloud layer. The Atacama Large Millimeter Array later recalibrated its receivers, reducing the signal to levels approximately 20 times smaller. Independent analyses found the original detection was likely sulfur dioxide misidentified by the data reduction pipeline. Headlines that had announced the possible discovery of Venusian biology disappeared from front pages. The corrections circulated mostly among scientists already following the story. The K2-18b dimethyl sulfide claim arrived in this context, and the pattern repeated, a 3 sigma announcement using the words revolutionary, a counter-analysis finding no signal at all. Public excitement followed by specialist dispute, with the dispute receiving a fraction of the coverage given to the original claim. Researchers studying how science communicates with the public have a name for the cumulative effect of this pattern. It creates a residue of unearned belief, a persistent public impression that alien life has been nearly or tentatively found, which no amount of careful subsequent correction fully removes. The incentive structure that produces these announcements is not difficult to understand. High-profile biosignature claims generate press coverage that drives funding conversations, secures telescope time, and builds the kind of public attention that universities and grant bodies respond to. The scientists making these announcements are not acting irrationally within the system they inhabit. They are responding accurately to its rewards. What the system does not reward is the quieter, slower work of confirming a signal through independent methods before announcing it. That work reduces the chance of embarrassment, but also reduces the chance of being first. The Green et al. Assessment framework, developed in 2021 and expanded in 2025, requires researchers to answer 5 questions before announcing a biosignature detection, including whether the signal is authentic, whether it has been correctly identified, whether abiotic sources have been adequately ruled out, whether life would plausibly produce it in the observed environment, and whether independent lines of evidence support the interpretation. The K2-18b claim, by the honest assessment of researchers who helped build that framework, failed at the first question. The signal's authenticity remained genuinely in dispute, but the announcement had already reached hundreds of millions of people, most of whom never encountered the dispute that followed. The pattern of premature announcements, the 5-question framework that K2-18b failed at the first question. The hundreds of millions of people who heard the claim and never encountered the correction. All of this was happening in a field that had possessed, since 1977, direct evidence that its foundational premises were wrong. The argument about dimethyl sulfide and instrumental systematics and retrieval methodologies was a sophisticated dispute happening on top of a much older and much simpler problem that the field had never fully addressed. The habitable zone framework told researchers where to look. The vents told researchers, 48 years earlier, that the framework was built on an incorrect assumption about what life required. The framework persisted anyway. On February 17, 1977, a research team led by Jack Corliss aboard the submersible Alvin descended to the floor of the Pacific Ocean near the Galapagos Islands at a depth of roughly 8,000 feet. The expedition had been searching for hydrothermal activity predicted by plate tectonic theory, warm water seeping up through cracks in the seafloor. What they found was something no biologist had predicted and no theory of life had left room for. Towering columns of superheated water, up to 700 degrees Fahrenheit, erupted from the seafloor into absolute darkness. Surrounding those vents were communities of organisms on a scale and variety that should, according to every prior understanding of how deep ocean ecosystems worked, have been impossible to sustain. Giant tube worms, later identified as Riftia pachyptilla, grew to nearly 8 feet in length and contained no digestive system. Clams of unusual size, crabs, fish, an entire food web operating in a place where no light from above had ever reached and where pressures would crush any human being without mechanical protection. The energy source for this entire ecosystem was not light. It was hydrogen sulfide converted into food through chemosynthesis, performed by bacteria that formed the base of a living community powered entirely by the chemistry of the Earth itself. Corliss understood immediately that this changed something fundamental. Life did not need the star. Life did not need a surface. Life did not need mild temperatures or moderate pressures or any of the conditions the habitable zone framework was built around. It needed energy and chemistry, and the seafloor provided both in forms that photosynthesis had never touched. The discovery was published and received significant scientific attention. It prompted a series of follow-up expeditions. It generated genuine excitement about the range of conditions life could tolerate. It did none of the things it should have done to the search for extraterrestrial life. James Casting formalized the circumstellar habitable zone in 1993, 16 years after the Corliss expedition. The framework he published in Icarus treated surface conditions as the organizing principle. Liquid water on a planetary surface, warmed by a star at the right distance, defined the searchable region of any given stellar system. The discovery that entire ecosystems could exist in crushing darkness, driven by geothermal chemistry rather than stellar energy, received no formal incorporation into that framework. The vents were acknowledged as interesting, as a curiosity, as evidence that life was more robust than assumed. They were not treated as evidence that the framework itself was examining the wrong conditions. The omission had a practical consequence. Europa was 5 times as far from our star as Earth, well outside the habitable zone by every calculation. Beneath its ice shell, tidal forces generated by Jupiter's gravity were almost certainly heating a global ocean. That ocean sat in contact with a rocky seafloor that could support hydrothermal activity, identical in principle to what Corliss had found on Earth's ocean floor. The vents changed everything about how to evaluate Europa. The framework said it was irrelevant. For 2 decades, the framework won. What this meant for the search was not merely that researchers looked in the wrong places. It meant they built instruments, proposed missions, and allocated billions of dollars around a set of assumptions that a submersible crew had disproved before the framework was even written. The tube worms near the Galapagos vents were only the beginning of what the following decades would reveal. By 2025, the catalogue of life existing in conditions that any prior conception of habitability would have declared lethal had grown so extensive that researchers began to ask whether the concept of an uninhabitable environment was coherent at, or organisms had been found in the cooling water of nuclear reactors. Bacteria had been cultured from rocks 3 miles underground, isolated from the surface world for millions of years. The most systematically studied example of extreme biology was also the simplest to describe, a phylum of microscopic animals whose tolerance for hostile conditions had, by any reasonable measure, outpaced every other multicellular organism on Earth. Tardigrades, sometimes called water bears for their lumbering gait under a microscope, are roughly 0.5 millimeter long and live in soil, moss, and leaf litter on every continent, including Antarctica. They were first described by the German pastor Johann August Ephraim Gozzi in 1773, who noted their unusual appearance but had no way of knowing what else was unusual about them. The chemistry by which they survive extreme conditions involves a suite of protective proteins that replace cellular water during desiccation, preventing the ice crystal formation that ruptures other cells during freezing. In a desiccated state, they enter cryptobiosis, a metabolic suspension so complete that their biological activity drops to near zero. In that state, they have survived temperatures from minus 272 degrees Celsius to 150 degrees Celsius. They survive pressures 6 times those at the deepest point of the ocean. They have survived direct exposure to the vacuum of space, to ultraviolet radiation at intensities that would kill any other animal, to ionizing radiation more than 1,000 times the lethal dose for a human being. In 2007, the European Space Agency mounted an experiment called Biopan-6 aboard the Photon M3 satellite. Tardigrades were attached to the exterior of the vehicle and exposed, unprotected, to the conditions of low Earth orbit for 10 days. Direct solar radiation in space carries ultraviolet wavelengths filtered out by Earth's atmosphere. Many of the specimens exposed to that full spectrum died. A significant fraction survived, and some of those survivors went on to reproduce normally after return to Earth. This was not a controlled laboratory demonstration of survival under artificial extreme conditions. It was direct space exposure, the actual environment of orbital vacuum and unfiltered stellar radiation. Multicellular animals survived it. The broader extremophile literature was, by 2024, documenting findings at a pace that made any simple summary immediately incomplete. More than 100 new species of pressure-tolerant bacteria had been recovered from the Mariana Trench at depths exceeding 6 miles, living under pressures greater than 1,100 atmospheres. Organisms in Antarctica's dry valleys, where perchlorate in the soil, ultraviolet radiation, extreme cold, and near-total absence of liquid water create conditions closely analogous to Martian surface environments, had been catalogued in 50 new taxa in that year alone. In Chernobyl's most contaminated reactor buildings, the fungus Cladosporium chernobylensis was not merely surviving elevated radiation but growing toward it, using melanin pigments to convert gamma rays into chemical energy, and in a borehole, 975 meters below the surface in Sweden, researchers had found Candidatus desulforudis audaxviator, a bacterium that appeared to constitute a one-organism ecosystem entirely independent of any energy source derived from the surface world, fueled instead by radiolysis of water and sulfate chemistry in the rock itself. These were the organisms that should have been shaping every conversation about where life could exist elsewhere. Researchers studying ocean worlds and exoplanet atmospheres were aware of them. The frameworks guiding mission selection were slower to adjust. The 7 ocean worlds in our solar system that have been confirmed or are considered strong candidates share a single property. None of them are where the habitable zone framework would have predicted life. Europa orbits Jupiter at a distance of about 414,000 miles from the planet, circling it once every 3.5 days. The tidal forces from Jupiter's gravity flex the Moon continuously, and that flexing generates heat. Beneath a shell of ice, estimated between 6 and 19 miles thick, lies a global liquid ocean that models suggest extends between 60 and 100 miles deep. That is more liquid water than exists in all of Earth's oceans combined, and it sits in direct contact with a rocky seafloor where the same tidal heating that warms the ocean above might drive hydrothermal activity similar to the vents Corliss found in 1977. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, returned magnetic field measurements that could only be explained by a conducting fluid beneath the ice, confirming the ocean's existence beyond serious scientific dispute. Enceladus is a moon of Saturn, roughly 300 miles across, so small that early estimates suggested its interior must be frozen solid. Cassini proved otherwise. In 2005, the spacecraft detected a series of active geysers erupting from the Moon's south polar region, shooting water ice particles, water vapor, and organic compounds into space at velocities high enough to escape the Moon's gravity and contribute to Saturn's outer ring. Cassini flew through those plumes directly and measured their composition. The results were unambiguous and extraordinary. The plumes contained liquid water, silica nanoparticles indicating hydrothermal reactions at roughly 90 degrees Celsius in contact with rock, molecular hydrogen at concentrations suggesting active serpentinization reactions, complex organic molecules of masses exceeding 200 atomic mass units, nitrogen, carbon dioxide, and methane. This was a direct in-flight chemical sampling of the material coming from an active subsurface ocean, and it contained essentially every ingredient researchers had proposed as necessary for life to begin. Enceladus was ranked as the highest priority target for a dedicated life detection mission in the most recent Planetary Science Decadal Survey. It remains unvisited by a mission specifically designed to evaluate its biology. Titan, the largest moon of Saturn, belongs to a different category. It has a nitrogen atmosphere denser than Earth's at its surface, and its surface chemistry runs on liquid methane and ethane rather than water. The Cassini-Huygens mission, which dropped a probe onto Titan's surface in January 2005 and spent 13 years characterizing the moon from orbit, found river deltas, hydrocarbon seas, and a full meteorological cycle in which methane evaporates, forms clouds, precipitates as rain, and flows back to the lowlands through channels eroded into bedrock of water ice. There is no liquid water on Titan's surface. Its surface temperature is -179 degrees Celsius. By every measure the habitable zone framework was designed to apply, it should be an irrelevant background object. Instead, the Dragonfly rotorcraft lander is scheduled to arrive there in 2034 because the scientific consensus is that Titan's surface chemistry is interesting enough to justify one of the most complex planetary science missions ever approved. The 7 ocean worlds, their existence confirmed after the habitable zone framework was built, represent a direct empirical test of that framework. They all fail it in the same direction toward habitability in conditions the framework did not consider. The question that Titan specifically posed to the concept of universal biochemistry had been articulated most precisely by researchers at Cornell University in 2015. James Stevenson, Jonathan Looney, and Paulette Clancy published a paper in Science Advances describing what they called the azotosome, a proposed cell membrane analog capable of functioning at cryogenic temperatures in liquid methane. On Earth, cell membranes are phospholipid bilayers made of molecules with a water-soluble head and a water-repelling tail that self-assemble into the thin sheets enclosing every living cell. That self-assembly requires water as the medium. It does not work in liquid methane. The Cornell team argued that small nitrogen-containing compounds called acrylonitriles, detected in Titan's atmosphere in abundance by Cassini data and later confirmed in spectroscopic observations, could form similar bilayer structures in liquid methane through what they termed hydrophobic equivalent interactions. The resulting membrane would, in computer simulations, be stable at Titan's surface conditions, flexible enough to function, and capable of enclosing internal chemistry in the way that phospholipid membranes do in Earth's cells. The proposal was explicitly theoretical, and the researchers said so. Acrylonitriles are present in Titan's atmosphere. The self-assembly behavior is a simulation. No sample collection, no laboratory experiment, and no mission has yet confirmed whether these structures form spontaneously under actual Titan conditions. What the azotosome hypothesis illustrated was a principle with consequences that extended far beyond Titan. If the chemistry of cell membranes is contingent, if Earth's choice of phospholipids was a historical path taken through one set of conditions that happened to be present on early Earth, then the search for membranes in other environments needed to stop looking for phospholipids and start asking what membrane chemistry the local chemistry made available. Jonathan Lunin, who had been studying Titan's chemistry for decades and was involved in both the Cassini mission planning and the azotosome paper, had argued for years that the fundamental biochemical assumptions built into the search needed revision. Life on Titan, if it existed, would not use photosynthesis, because Titan receives roughly 1% as much energy from our star as Earth does, and that energy arrives in a spectrum dominated by infrared rather than visible light. The metabolism Lunin proposed involved acetylene reacting with hydrogen to produce methane, a pathway analogous to the hydrogen sulfide metabolism at Earth's hydrothermal vents, in the sense that it ran on local chemistry rather than stellar radiation. The waste product would be methane, which Titan's atmosphere already contains in quantities Cassini measured carefully. One implication follows: if something metabolizing acetylene existed in Titan's atmosphere or on its surface, its waste products would be chemically indistinguishable from the methane produced by entirely abiotic photochemical processes. The life, if present, would be invisible to the detection methods Cassini carried. This was not a failure of the mission. It was an illustration of a problem that appeared everywhere the search pushed into genuinely unfamiliar chemistry. The Dragonfly rotorcraft arriving at Titan in 2034 will carry instruments designed to search for prebiotic chemistry rather than life itself, which is a deliberate choice shaped by this exact recognition. What Dragonfly can measure are the molecular building blocks of biochemistry, the complex organic compounds called tholins that Cassini found blanketing Titan's surface, and the question of how far along the path towards self-organizing chemistry those compounds have traveled. But if Titan hosts something that has crossed from chemistry into biology using nitrogen-based membranes and acetylene metabolism, it is not obvious that Dragonfly's instruments would recognize it. The detection problem on Titan is not instrumentation. It is that searching for life requires knowing what you are looking for, and everything known about what life looks like comes from a single example that used completely different conditions. The azotosome hypothesis did not resolve this problem. It illustrated how deep it runs. The Venus phosphine story did not end where the official narrative placed its ending. Jane Greaves of Cardiff University announced the detection of phosphine in Venus's atmosphere on September 14, 2020, in a paper published in Nature Astronomy. Phosphine, a molecule of one phosphorus atom bonded to 3 hydrogen atoms, had a specific significance in the biosignature literature. On Earth, it is produced in meaningful quantities only by microbial organisms in anaerobic environments and, to a small degree, by industrial synthesis. Greaves and her colleagues had found it at a concentration of approximately 20 parts per billion in the cloud layer, at an altitude of roughly 34 miles above Venus's surface, where pressure and temperature conditions are comparable to Earth's lower atmosphere. The announcement generated coverage on the same scale as the K2-18b claim 5 years later. The collapse of the detection followed a path similar to what would happen with K2-18b. The Atacama Large Millimeter Array, which had provided the primary data, was subsequently recalibrated, and when the same observations were processed with corrected calibration files, the phosphine signal dropped by a factor of roughly 20, pushing it to levels that could be explained by sulfur dioxide misidentified by the initial data reduction pipeline. Independent analyses by multiple groups found no phosphine when they used different methodologies. The field arrived at a rough consensus that the original claim had overstated the evidence considerably. The correction received, as these corrections consistently do, a fraction of the coverage the announcement had generated. What the field did not do was formally close the question. The James Clerk Maxwell Telescope on Mauna Kea, Hawaii, which had contributed to the original detection, continued observing Venus over subsequent years. By 2024, results from the ongoing observation program showed phosphine signatures that appeared to follow Venus's day-night cycle, weakening where the cloud layer was exposed to stellar radiation, and strengthening in the shadow region where photodissociation could not occur. That pattern is exactly what a replenished source, something actively producing the molecule and having it destroyed faster on the day side than the night side, would produce. A photodissociation product of sulfur dioxide would not show that same asymmetry in the same way. In parallel, ammonia had been tentatively detected in Venus's clouds, another molecule with no well-established abiotic source in that environment. The detection that was officially debunked was, in practical terms, producing follow-up results that declined to cooperate with the debunking. And as of early 2026, the question of what was producing whatever signal was present in Venus's cloud layer remained genuinely unresolved rather than settled. Part of the reason the question persisted is that the temperate cloud layer Greaves originally identified as a candidate environment is, by several measures, genuinely unusual. At the altitude of roughly 30 to 40 miles above Venus's surface, pressures are close to Earth's at sea level, and temperatures range between 30 and 70 degrees Celsius, conditions that would not immediately kill a bacterium native to Earth. Research published from the Massachusetts Institute of Technology showed that certain amino acids remain chemically stable even in concentrated sulfuric acid, which is the main component of Venus's cloud droplets, overturning an assumption that the acidity ruled out organic chemistry entirely. Rocket Lab was planning an atmospheric entry probe mission to Venus specifically designed to examine the cloud layer chemistry in situ, a mission that the contested phosphine detection had helped motivate. Venus, the planet dismissed as certainly dead after the phosphine signal was attributed to a calibration error, had acquired enough unresolved questions by 2026 to justify missions that would not exist had the retraction been the final word. Silicon occupies the position directly below carbon on the periodic table, which is a chemical shorthand for saying it shares many of carbon's bonding properties. It forms 4 chemical bonds. It can build long chains and rings. It is enormously abundant, the second most common element in Earth's crust. Julius Scheiner proposed in 1891 that silicon might serve as the basis for life on other worlds, and the idea has been revived periodically ever since. Most recently given more rigorous chemical treatment by William Baines and colleagues at Imperial College London in a 2018 paper in the journal Life. The intuitive appeal is straightforward. If carbon's exceptional ability to form complex molecules is what makes it the basis of terrestrial biochemistry, silicon's similar bonding characteristics make it a logical candidate for life in environments where carbon chemistry struggles. The obstacles are specific and real, which makes them more useful to understand than a general dismissal. Silicon-oxygen bonds, which form when silicon is exposed to water or oxygen, are extraordinarily stable. They produce silicon dioxide, which is quartz, which is rock. where carbon reacts with oxygen to form carbon dioxide, a gas that dissolves in water and participates dynamically in biochemical cycles. Silicon reacts to form solid minerals that precipitate out of solution and become geologically inert. Silicon-silicon bonds, the analog of the carbon-carbon bonds that form the backbone of organic chemistry, are highly reactive in the presence of water and unstable under conditions where carbon chains are completely comfortable. Silicon-hydrogen bonds hydrolyze rapidly in aqueous environments. The chemistry that makes carbon so versatile in the water-based conditions of Earth's surface is chemistry that silicon simply cannot perform in that same medium. The more productive question is whether different conditions could change that calculation. Baines and colleagues noted that silicon might find biochemical application in non-aqueous environments. Liquid sulfuric acid, which is the dominant solvent in Venus's cloud layer and potentially relevant to certain classes of planetary atmospheres, behaves very differently from water as a chemical medium, and some silicon chemistry that is impossible in water becomes viable in sulfuric acid environments. The proposal is speculative and untested by any experiment involving actual planetary conditions. Its significance is less as a prediction about where silicon life might exist than as a demonstration of what happens when the assumption of water as the universal biochemical solvent is relaxed. Change the solvent, and the list of elements capable of supporting complex chemistry changes with it. Carbon's dominance is inseparable from water's dominance. A universe where other solvents are common is a universe where the periodic table of potentially life-supporting elements becomes considerably longer. Liquid ammonia provides a parallel example. It is a polar molecule capable of dissolving many of the same compounds that water dissolves. It exists as a liquid between -77 and -33 degrees Celsius at Earth-like pressures, which are conditions present on any planet or moon sitting far enough from its star for water to freeze. Titan's interior almost certainly contains an ammonia-water mixture beneath its hydrocarbon surface, and ammonia-rich subsurface liquids are implicated in the chemistry of several outer solar system moons. An organism adapted to liquid ammonia as its primary medium would look chemically alien in almost every respect, because most of the reaction pathways that function well in water perform very differently or fail entirely in ammonia. Carl Sagan, who described himself as a carbon chauvinist, acknowledged that the bias went deeper than just element selection. It extended to solvent, to temperature range, to the assumption that complexity required the specific conditions that produced complexity on Earth. The search had been designed to find one specific version of life in one specific set of conditions. The universe was under no obligation to cooperate. Every amino acid found in living organisms on Earth is left-handed. The molecule can exist in either mirror form, left or right, with identical chemical composition and bonding structure. But spatial arrangements that are non-superimposable reflections of each other, the way a left glove and right glove are the same shape in opposite orientations. Earth's life made a choice early in its history, or the chemistry of life's origin favored one orientation. And every organism that has ever lived on this planet has used left-handed amino acids and right-handed sugars without exception. There is no known chemical necessity that required this choice. The two orientations are equally stable under ordinary conditions. The selection of one chirality over the other appears to be a historical accident, a frozen accident, as Francis Crick described it in 1968, a contingency locked in place early in evolution that has persisted because life's molecular machinery, once calibrated for one chirality, cannot simply switch to the other without catastrophic incompatibility in every cellular process simultaneously. Paul Davies of Arizona State University raised the implications of this at a meeting of the American Association for the Advancement of Science in February 2009. If life arose multiple times on early Earth, which the speed of life's emergence after the planet's formation makes plausible to some researchers, then some lineages might have used the opposite chirality. Those lineages could have been outcompeted by the dominant biochemistry in environments where the two came into contact, but they might have persisted in isolated niches. Organisms using right-handed amino acids and left-handed sugars would be biochemically incompatible with all known life. They would not infect it, could not eat it, and would not be eaten by it. More importantly, they would be invisible to virtually every detection method available. Metagenomic sequencing, which works by reading genetic sequences, is calibrated for the 4-base DNA code of known life. Mass spectrometry for amino acid detection is designed around the specific molecular weights and fragmentation patterns of left-handed versions. The microscopy techniques used to image microorganisms do not inherently distinguish chirality. Shadow life. As Carol Cleland and Shelley Copley of the University of Colorado Boulder named this concept in their 2005 paper in the International Journal of Astrobiology, would pass through every standard survey of microbial diversity without registering. The absence of evidence in those surveys would prove only that our instruments cannot find it, not that it is absent. The practical difficulty in searching for shadow life on Earth is itself a clue about the scale of the problem facing the search beyond Earth. Surveys of environmental microbial diversity regularly recover genetic sequences from soil, ocean water, and deep subsurface samples that do not match any known branch of life. These sequences, sometimes called microbial dark matter by researchers such as Gillian Banfield at the University of California, Berkeley, account for roughly 15% of the gene sequences in some environmental samples. They may simply represent organisms whose genomes have not yet been fully characterized. They might also represent something more interesting. A 2022 paper in Frontiers in Microbiology noted directly that shadow life, if it existed, might be among us and remain undetected simply because the tools microbiologists use were calibrated to find what they already know. No systematic survey designed specifically to find chirally inverted life has ever been conducted, because building an instrument sensitive to right-handed amino acids requires deciding first to look for them. The decision to look for only what we already recognize has been the operational default of the search, on Earth and beyond it. The genetic alphabet of every known organism on Earth uses 4 chemical letters: adenine, thymine, guanine, and cytosine, arranged in specific pairs across the double helix of DNA. This is the universal code, shared without exception across bacteria, archaea, and all complex life. The universality has been interpreted as evidence that life had a single origin, that this specific system was selected for reasons that may reflect genuine chemical superiority, and that life elsewhere, if it uses nucleic acids at all, would likely converge on something similar. None of these interpretations are wrong, exactly, but each smuggles in an assumption that laboratory chemistry has been systematically testing and finding porous. The Benner Group at the Foundation for Applied Molecular Evolution and researchers at the Medical Research Council Laboratory of Molecular Biology in Cambridge have built alternative genetic systems using chemically modified backbone, molecules, and expanded or contracted sets of base pairing letters. Threose nucleic acid, known as TNA, uses a 4-carbon sugar instead of the 5-carbon sugar in RNA, and it can fold into functional structures and copy itself under appropriate conditions. Peptide nucleic acid replaces the sugar phosphate backbone with a protein-like peptide chain and can store and transmit genetic information. Glycol nucleic acid uses an even simpler glycol backbone. These are not theoretical proposals awaiting laboratory validation. They have been synthesized, studied, and in several cases demonstrated to support Darwinian evolution in controlled experiments. Hachimoji DNA, developed by Stephen Benner and published in Science in 2019, expanded the genetic alphabet to 8 bases and produced a system capable of encoding information at higher density than standard DNA while maintaining the double helical structure. The implication is not complicated. If genetic systems using different backbone molecules, different sugars, and different numbers of base pairing letters are all chemically viable, and if life on Earth settled on one of them through a historical selection event rather than because of chemical necessity, then alien life using a different system would be undetectable by every method currently deployed in the search. Genomic sequencing instruments are calibrated for the 4-base code. The primers used in polymerase chain reaction amplification of environmental DNA are designed to bind specific sequences in the standard alphabet. A sample from Enceladus's plume processed through a standard genomics instrument would return negative results for any life using a different genetic code, and the negative result would be accurate only in the narrow sense that no DNA-based life was present. The result would say nothing about whether some other hereditary system was functioning in the same sample. The RNA world hypothesis, proposed by Walter Gilbert in 1986, suggests that the earliest life used RNA both to store information and to catalyze chemical reactions before the division of labor between DNA and proteins was established. The ribosome, the molecular machine that builds proteins in every cell on Earth, is fundamentally an RNA enzyme, preserving what appears to be a trace of this earlier era. But RNA is chemically unstable, prone to hydrolysis, and difficult to synthesize under the conditions of early Earth chemistry without already having enzymes to assist the process. The biochemist Gerald Joyce, working with Leslie Orgel, called it the prebiotic chemist's nightmare. Alternative hypotheses propose that life began with self-sustaining chemical networks, metabolism without genetic molecules, driven by mineral surfaces at alkaline hydrothermal vents where proton gradients provided energy. If the metabolism first view is correct, then alien life might operate through chemical networks that have never developed discrete genetic molecules at all, leaving no nucleic acids to sequence, no codons to translate, and no DNA for any instrument to recognize. The entire framework of genomics as a detection method would be irrelevant to it. In the night sky over the Roque de los Muchachos Observatory on La Palma in October 2016, a faint object crossed the field of a survey telescope at a trajectory that immediately told astronomers it was moving too fast to be bound to our star's gravity. The object, later named Oumuamua, was the first confirmed visitor from another star system, and its passage through the inner solar system confirmed something that had been understood theoretically but never directly observed. The space between stars is not empty of solid material. Objects form around other stars and get ejected, and some fraction of them eventually pass through other systems. The rate at which this happens, combined with estimates of how many solid objects drift freely through interstellar space, suggested that material from distant stellar systems moves through the galaxy continuously and has been doing so for billions of years. The population of rogue planets, worlds, ejected entirely from their birth systems during the chaotic early phase of planetary architecture, has been estimated for years as enormous. Gravitational interactions between forming gas giants can fling smaller planets into interstellar space before those planets ever settle into stable orbits. Estimates put the number of rogue planets in the Milky Way at somewhere between several hundred billion and several trillion, a figure that could plausibly exceed the number of stars. These worlds receive no stellar energy. Their surfaces are frozen at temperatures near absolute zero. For years, they were treated as obviously sterile, and the reasoning was simple. Without a star, there is no energy, and without energy, there is no life. In December 2025, a research team at the Konkoly Observatory in Hungary published results in astronomy and astrophysics that directly challenged the assumption that rogue planets were necessarily dead. Their simulations of moon-planet systems ejected from stellar systems showed that in 12 to 15% of cases, tidal interactions between a rogue planet and an orbiting moon maintained geothermal heating comparable to what drives Europa's ocean for timescales exceeding the current age of the solar system. A moon orbiting a rogue planet at the right orbital distance and eccentricity would flex under tidal forces exactly as Europa does, generating heat in its interior, potentially maintaining a subsurface ocean beneath an ice shell for billions of years with no star anywhere nearby. Separate observations from the James Webb Space Telescope in 2024 had found 6 free-floating planetary mass objects with protoplanetary disks, the flat rings of material from which moons and smaller planets form, surrounding objects drifting alone through interstellar space. The silicate grain emissions detected in those disks showed dust growth and crystallization, the earliest stages of rocky body formation. Belinda Damian, a researcher involved in the JWST free-floating object study, noted that the building blocks for forming planets could be found even around objects barely larger than Jupiter drifting alone in space. Moons were apparently forming around wandering worlds in the dark. The search had been designed around stars. The largest population of potentially habitable worlds in the galaxy may have nothing to do with stars at all, and every instrument built to find habitable zones around stellar systems was, by design, completely blind to them. The Murchison meteorite fell in the morning hours of September 28, 1969, over a small town in Victoria, Australia, scattering fragments across several square miles of farmland. It was a carbonaceous chondrite, a type of meteorite preserving chemistry from the early solar system, largely unaltered by geological processes, and the scientific community recovered it quickly enough to prevent extensive contamination. Analysis over the following years, refined repeatedly as techniques improved, eventually identified more than 70 amino acids in its composition. 19 of those amino acids are found in living organisms on Earth. More than 50 are not. They form in space, in interstellar chemistry driven by ultraviolet radiation and grain surfaces, without any biology involved, in quantities sufficient to survive delivery to a planetary surface during an impact event. The question of whether those building blocks contributed to life on Earth was addressed directly in a 2024 paper by David Cow, Peter Plavchan, and Michael Summers of George Mason University, published in the Astrophysical Journal. Their analysis of impact rates during Earth's early history estimated approximately 200,000 collision events between Earth and extraterrestrial objects before the earliest confirmed evidence of life. The conditional probability that panspermia specifically seeded Earth's life, rather than Earth's life arising independently from chemistry that meteorites may have supplemented, they calculated at less than 1 in 100,000. Earth almost certainly generated its own life from chemistry it already had, supplemented perhaps by organic material arriving from space but not sparked by organisms arriving from elsewhere. The more interesting number in their analysis was different. When they applied the same impact rate calculations to the broader galaxy, they found that panspermia may have seeded living organisms onto as many as 100,000 worlds in habitable zones across the Milky Way. Not Earth specifically, the galaxy in general. The 2019 detection of isopropyl cyanide in the molecular cloud Sagittarius B2, located 25,000 light-years from Earth, confirmed that branched carbon molecules capable of serving as amino acid precursors assemble in interstellar space before any planet forms. The Stardust mission had returned cometary glycine from Comet Wild 2 inches 2006, demonstrating that amino acids survived not just interstellar synthesis, but also the violence of comet formation and the heat of re-entry in a sample return capsule. The chemistry of life's building blocks appears to be a routine product of stellar and interstellar processes, distributed across the galaxy in the material from which every new planet forms. Whether any of those building blocks anywhere else took the next steps towards self-replication, metabolism, and selection is the question the search was always actually trying to answer. The framework built to answer it had been designed around a single example, a single chemistry, and a single type of world. The universe had not constrained itself to those terms. What the panspermia research collectively suggested, taken beyond any individual finding, was that the question the search had been organized around since Frank Drake sat at his radio telescope in 1960 was structurally incomplete. The search had been asking where life existed. The research on ocean worlds, extremophiles, alternative biochemistries, rogue planets, and interstellar organics had been asking something different and more uncomfortable. What assumptions was the search making about what life was, what it required, and what it would look like when found? Each of those assumptions, examined in isolation, had turned out to be contingent rather than necessary. Life could run without starlight, as the vents demonstrated. It could function at temperatures and pressures the habitable zone framework excluded, as tardigrades and vent organisms showed. It could build membranes from nitrogen, encode information in molecules other than DNA, and potentially drift between stars. None of this proved life was common. All of it proved that the framework designed to find it had been built from a single example and treated that example's specific characteristics as universal requirements. The chapters ahead would ask what happened when the field tried to correct for that, and whether it was already too late for some of the searches already underway. The corrections the field needed had been building for decades, but none of them answered the most basic question the search had been designed to answer from the beginning. On the evening of August 15, 1977, a volunteer astronomer named Jerry Amon was reviewing a paper printout of data collected by the Big Ear Radio Telescope at Ohio State University when he encountered a sequence of characters that made him stop. Big Ear did not record audio. It sampled radio signal strength at the hydrogen line frequency, 1420 MHz, and printed the results as a sequence of numbers and letters. Signal strengths from 1 through 9 were printed as numerals. Anything stronger than 9 was printed as a letter, A for 10, B for 11, C for 12. The printout in front of Eman showed the sequence 6EQUJ5. The peak, the letter U, represented a signal strength 30 times above the background noise level. Eman circled it and wrote a single word in the margin with a red pen: wow. The signal had arrived from the direction of the constellation Sagittarius. It had lasted exactly 72 seconds, which is precisely the duration a fixed source of radio emission from deep space would remain in Big Ear's field of view as Earth's rotation swept the beam past it. It occupied a narrow range of frequencies centered on the hydrogen line, the frequency Frank Drake had identified in 1960 as the universal radio channel any technologically capable civilization would know to monitor. Everything about its characteristics matched what researchers had theoretically expected an artificial signal from another civilization to look like, and researchers said so when the discovery was eventually discussed publicly. Big Ear staff, and then dozens of researchers from other institutions, spent hundreds of hours searching for a repeat. The telescope returned to the same region of sky for years. Other radio observatories joined the follow-up effort. In the decades since, no signal matching the WOW characteristics has ever been detected from that location, or from any location, despite the accumulated observing time of the global radio astronomy network. The signal was never confirmed. It was never explained. A team led by Antonio Paris of St. Petersburg College proposed in 2017 that the signal might have originated from a hydrogen cloud surrounding a comet passing through the telescope's field of view that night. But other researchers found the geometry and frequency characteristics of that explanation unconvincing. 48 years after Eman's pen touched that printout, the WOW signal remains the most credible candidate for an artificial extraterrestrial signal in the history of the search. And the reason it is the most credible candidate is also the reason it cannot be confirmed. It appeared once, lasted 72 seconds, and never appeared again. The practical lesson encoded in that night's data went without formal incorporation into how the search was redesigned. A signal that arrives once and vanishes is unverifiable by the methodology the field requires for confirmation. The detection must be reproducible, ideally by independent observers pointing separate instruments at the same source. A civilization broadcasting toward Earth for 72 seconds, and then stopping, or broadcasting continuously but from a source in motion, or using a narrow enough beam that Earth's rotation would carry it out of range before a second telescope could lock on, would leave exactly the kind of record the WOW signal left. The field's confirmation requirements were built around the scientific need for reproducibility. They were not built around the possibility that a genuine signal might be structurally incompatible with those requirements. Whether the WOW signal was real, the fact that it remained unresolved was itself an answer, just not the one the search had been designed to produce. 42 years after the WOW signal produced a result the field could not confirm, the most technically sophisticated private search in the history of radio astronomy encountered the same problem in a more instructive form. The Breakthrough Listen initiative had been running since 2015, funded by Yuri Milner's $100 million commitment and operating some of the most powerful radio telescopes on Earth. In April and May 2019, the Green Bank Telescope in West Virginia recorded a narrowband signal at 982 MHz during a series of observations targeting Proxima Centauri, the nearest star to our own stellar system, at just over 4 light-years away. The signal appeared in 5 separate 30-minute observation windows. It disappeared each time the telescope was pointed away from Proxima Centauri and reappeared when the telescope returned to that direction. Proxima Centauri hosts at least one confirmed planet, Proxima b, an Earth-sized world orbiting within the star's habitable zone. The detection sat unpublished for more than a year, while the Breakthrough Listen team worked to rule out terrestrial explanations. Sophia Sheikh, a graduate student at Pennsylvania State University who led the analysis, described the signal's behavior as exactly what a transmission from the vicinity of a nearby star would be expected to produce. The frequency, the directionality, and the timing all matched a credible artificial extraterrestrial origin. The team named it Breakthrough Listen Candidate 1. Then Sheikh's team examined the signal's frequency drift. A radio transmission from a planet in orbit around a star experiences a Doppler shift. As the planet moves toward or away from the receiver, the signal frequency changes in a predictable direction. A planet orbiting a star in a configuration consistent with Proxima b's known parameters would produce a signal drifting downward in frequency, decreasing over time as Earth's rotation and the source planet's orbital motion interacted. The BLC1 signal drifted upward. Sheikh described the discrepancy in a vivid comparison. The expected pattern was like a trombone slide being extended, pulling the frequency down, while the actual signal behaved like a slide whistle being pushed, going up instead. The direction was wrong for a planetary source. Further analysis identified the signal as an intermodulation product of human-made radio interference, a combination of terrestrial transmitters, creating a false signal that mimicked an astrophysical source at the telescope's receiver. The Breakthrough Listen team found dozens of similar signals in the same data, all sharing the same wrong direction drift, all traceable in principle to local interference. BLC1 was not a signal from the direction of the nearest star. It was electronic noise from the civilization on the surface of this one. What the episode demonstrated, and what Sheikh's team documented carefully in their published analysis, was that the detection protocol had functioned exactly as designed. The team held the candidate for over a year, applied systematic tests, and those tests identified a false positive before any public claim was made. The deeper lesson was about the scale of the filtering problem. Even at the nearest star, even with the most sophisticated private search facility ever built, even in the most favorable configuration of telescope and known planet, distinguishing a genuine signal from Earth's own electromagnetic interference required months of analysis and still produced ambiguous cases. Proxima Centauri is 4 light-years away. The galaxy is 100,000 light-years across. Every argument about the rarity of life, about the difficulty of detection, about the silence of the cosmos, eventually ran into the same wall. The Milky Way was old enough and large enough that a civilization which had achieved interstellar travel even a few million years ago could have colonized the entire galaxy by now. A few million years is an eye blink in the context of a galaxy 10 billion years old. The stars anchoring the outer disk of the Milky Way are 3 times as old as our own stellar system. If life arose anywhere in that outer disk early in the galaxy's history, and if even a small fraction of it reached technological capability and began expanding, the evidence of that expansion should be everywhere. Enrico Fermi articulated the paradox at a lunch table in Los Alamos in 1950 with a question that remains unanswered: where is everybody? Robin Hanson, an economist at George Mason University, published in 1998 the framework that gave the paradox its sharpest edge. He proposed that between the origin of simple matter and the emergence of space-colonizing intelligence, at least one step was so improbable that almost no lineage of matter ever completed it. He called this the Great Filter. Every planet that produces simple chemistry does not produce life. Every planet that produces life does not produce complex cells. Every planet that produces complex cells does not produce intelligence. Somewhere in that chain, a step exists that matter almost never gets through, and that step filters out essentially everything. Hansen's argument was that the silence of the cosmos, the absence of any detected civilization, was the empirical result that allowed this inference. If the filter were not very powerful, we would expect to see its survivors. The terrifying implication was not the filter's existence. It was the question of where in the chain the filter sat relative to humanity. If the improbable step was life arising from chemistry, then Earth was extraordinarily lucky and most planets are dead at the molecular level. If the filter was already behind the evolutionary chain that produced human beings, then we represented a kind of survivor's luck, having passed through the unlikely bottleneck. The universe would be silent because we were alone, or nearly so. The alternative reading was far worse. If simple life arose readily, if complex life followed without unusual improbability, if intelligence was a reasonably common outcome of evolution on suitable worlds, then the filter was ahead. Something regularly destroys civilizations after they achieve technology, with sufficient consistency that none of them has ever left a detectable trace. The silence would mean that intelligence was regularly eliminated before it could spread. Finding microbial fossils on Mars would shift this calculation toward that darker reading. If life once arose independently on Mars, then the origin of life was probably easy. The filter came later, and whatever it was still lay in front of us. Conversely, finding that Mars was absolutely sterile, that its chemistry had never crossed the threshold into biology despite billions of years of early liquid water, would suggest that life's origin was extraordinarily rare, that the filter might be behind us, and that we were something close to alone. The Europa Clipper, the Dragonfly mission, the Mars Sample Return Program, each of them was, in this framing, a search for the most important fact about humanity's future that any instrument had ever been designed to find. The Fermi paradox, as a formal mathematical problem, had a weakness that took several decades to identify clearly. The Drake equation required specific values for 7 independent variables. Most treatments plugged in estimates, multiplied them together, and arrived at a number, which was then used to argue either that the galaxy should be full of civilizations or that it should contain very few. The conclusion depended entirely on which estimates were chosen. Optimists chose high values and concluded the silence was mysterious. Pessimists chose low values and concluded silence was expected. Both groups were doing something mathematically equivalent to arguing about how many heads would come up in 1,000 coin flips when you did not know the coin's bias. The uncertainty about each factor was as important as the factor's central estimate, and almost no treatment of the equation propagated that uncertainty through the calculation. Anders Sandberg, Eric Drexler, and Toby Ord at Oxford's Future of Humanity Institute published a systematic treatment of this problem in 2018, using probability distributions for each Drake factor rather than point estimates. Instead of asking what number resulted from plausible values, they asked what distribution of outcomes resulted from uncertainty ranges consistent with the scientific evidence. The output was not a single number, but a spread of possible values, and that spread was consistent with the expected number of detectable civilizations in the observable universe being 0. The Fermi paradox might not be a paradox. Give an honest accounting of how little we knew about each factor in the chain from star formation to transmitting civilization. Silence was a statistically expected outcome. The field had built a mystery around a calculation that was always compatible with finding nothing. This did not prove the galaxy was empty. It demonstrated that silence did not demand an explanation beyond the uncertainty in the underlying biology and sociology. But the human instinct to explain the silence had generated a rich body of alternative reasoning. John Ball, at the Massachusetts Institute of Technology, had proposed in 1973 that advanced civilizations might intentionally avoid contact with emerging technological species, treating the galaxy's younger inhabitants the way a researcher treats an undisturbed ecosystem. Ball called it the zoo hypothesis. A darker framework, most accessibly articulated in the science fiction of Liu Cixin, proposed that the universe was a hostile equilibrium in which any civilization revealing its location invited destruction from others whose survival depended on eliminating potential competitors before they could grow powerful. Every civilization capable of understanding the situation kept quiet, and those that did not were eliminated. David Grinspoon at the Planetary Science Institute proposed what he called the inevitable expansion fallacy, the assumption that advanced civilizations would necessarily spread outward into space might simply be wrong. A civilization that achieved ecological sustainability, that managed its resources without exponential growth, might exist for billions of years without expanding, producing no detectable signature. The silence would then mean that the galaxy was full of long-lived civilizations that had chosen or been forced to remain small, quiet, and invisible. We would never know they existed, and they would never tell us. The radio telescope at Arecibo, Puerto Rico, was dismantled in 2020 when its support structure collapsed, ending 5 decades of service as the largest single-dish radio receiver in the world. In those 5 decades, the technology that had made radio transmission the dominant form of long-distance communication on Earth had largely moved past it. Fiber optic cables crossing the ocean floor carried voice, data, and video at capacities that made radio increasingly peripheral. Cell phone networks operated on frequencies carefully managed to minimize what escaped into space. Military radar systems, once the most powerful unintentional radio source Earth produced, were being supplemented by systems with narrower beams and shorter transmission windows. The electromagnetic footprint of human civilization, which had been expanding since the first commercial radio broadcasts of the 1920s, had begun to consolidate in ways that made it progressively less visible to any hypothetical observer watching from across the galaxy. If any civilization within a few hundred light-years had been pointing a radio telescope at Earth in the 1960s and 70s, it might have detected the strongest signal Earth's expanding radiosphere had ever produced. Those decades represented the peak of Earth's accidental broadcast signature, television transmissions, radar systems, and military communications leaking enormous amounts of radio energy into space without any intent to communicate. The signal Earth produces today is weaker and more coherent, increasingly concentrated in guided systems that do not radiate into space. The window during which Earth was maximally detectable may have lasted roughly half a century. That window may already be closing. This was the problem the search had built itself around without ever fully confronting. The equipment calibrated to detect civilizations broadcasting like mid-20th century Earth was calibrated for a technological signature that its own civilization was in the process of abandoning. A civilization that had used radio and then switched to guided optical networks would, to any external observer with radio telescopes, appear to go silent. That silence would look identical to the silence we have been observing in every direction we have pointed our instruments. Jill Tarter, at the SETI Institute, had argued for years that the field needed to broaden its conception of what signatures to search for. The category of techno-signatures extended far beyond radio. A civilization constructing large structures around its star would leave infrared excess detectable in sky surveys. A civilization modifying its planetary atmosphere with artificial compounds would leave chemical signatures no natural process produced, and chlorofluorocarbons were specifically unambiguous. There was no known geochemical or biochemical pathway that generated them at detectable concentrations without industrial synthesis. City lights on the night side of a transiting exoplanet were, in principle, detectable by sufficiently sensitive instruments. Laser communication carried information at higher efficiency than radio, but left a narrowly directed optical pulse invisible unless aimed near Earth. The field had been searching one frequency band, built around one technology, developed by one civilization, for less than a century. The universe was approximately 13.5 billion years old. The boundary between biology and physics had always been assumed to be cleaner than it turned out to be. In 2007, Gregory Engel and colleagues at the University of California, Berkeley published measurements of the Fenner-Matthews-Olson protein complex in green sulfur bacteria, a molecular structure that transfers energy from light-harvesting antenna proteins to the reaction center where photosynthesis occurs. The transfer efficiency of this system approached 100%, a level of performance that classical chemistry could not account for. At room temperature, in a living cell surrounded by thermal noise, energy should have been lost at every hop between molecules. Engel's group found quantum coherence. The energy was existing in superposition across multiple molecular pathways simultaneously, exploring all routes to the reaction center at once and selecting the most efficient one as the superposition collapsed. Photosynthesis, the biochemical process that had powered most of life on Earth for over 3 billion years, was partly a quantum mechanical phenomenon operating in warm, wet, noisy biological tissue. The avian magnetic sense had accumulated its own quantum evidence by this point. Migratory birds navigate using a compass that operates through cryptochrome proteins in their retinas, and the mechanism depends on radical pair formation, pairs of electrons whose spins become correlated in ways sensitive to magnetic field orientation. The correlation is maintained long enough to influence the protein's chemistry, allowing the bird to detect the direction of Earth's magnetic field with its visual system. The mechanism is fundamentally quantum, requiring electron spin states that remain entangled in a thermal environment where quantum effects should not survive. Yet European robins orienting their migrations, loggerhead turtles mapping ocean basins, all of them rely on a compass built from quantum entanglement inside a warm biological structure. The implications for the search for alien intelligence were speculative, but not without grounding. Stuart Hameroff at the University of Arizona and Roger Penrose at the University of Oxford had proposed since the early 1990s that consciousness itself might emerge from quantum processes in the microtubule networks inside neurons. Their orchestrated objective reduction theory proposed that quantum superpositions in these structures collapsed in ways that produced subjective experience, that the felt quality of thought was a quantum phenomenon occurring at the boundary between classical and quantum physics. The majority of neuroscientists remained skeptical, largely because the thermal noise of a biological cell seemed too disruptive to permit the quantum coherence the theory required. The photosynthesis findings had complicated that dismissal. Thermal noise had been judged sufficient to destroy quantum coherence in biology, and that judgment had proved incorrect in at least one critical system. Whether consciousness required quantum biology remained genuinely open, and the consequence was significant. If intelligence was inseparable from quantum processes in biological structures, then looking for radio transmitters and city lights was looking for the outputs of intelligence, while remaining blind to intelligence's possible physical substrate. The search had always been measuring what civilizations built. It had never measured what civilizations were. For 60 years, the search for life had been organized around a specific question: were conditions right for life here? The question implicitly assumed a definition. NASA's working definition had been in use for decades: a self-sustaining chemical system capable of Darwinian evolution. The definition was practical, the product of genuine effort to make the concept measurable, and it had oriented a great deal of productive research. It also had well-documented limitations. Viruses were not self-sustaining without a host. Pre-cellular chemistry, the kind of reaction network that may have preceded the first cell, was not obviously capable of Darwinian evolution in any discrete sense. The boundary kept shifting, and the definition kept being revised to exclude the most recent inconvenient example. Lee Cronin at the University of Glasgow and Sarah Walker at Arizona State University published a paper in Nature in October 2023, proposing a way around this definitional trap. They called it assembly theory, and its central concept was the molecular assembly index, a measurable quantity representing the minimum number of steps required to build a given molecule from its component atoms. Simple molecules have low assembly indices. They can form through a small number of chemical reactions from atoms occurring together by chance. Complex molecules with high assembly indices require many specific sequential steps, and those steps cannot all occur by chance in any realistic timeframe. A molecule with a high assembly index was almost certainly the product of selection, of a process that preserved and accumulated specific structures rather than allowing each step to be random. Cronin and Walker argued that a threshold assembly index, which they placed at roughly 15, was high enough that molecules above it essentially could not form without some selective process, whether biological or technological. The framework had a property distinguishing it from every prior approach to defining life. It made no assumptions about chemistry. It did not require carbon, water, or DNA, or any specific molecular structure. It asked only how many assembly steps were required to build the molecule in question. And that question could be applied to any chemistry in any environment using any detection instrument capable of measuring molecular complexity. A meteorite carrying molecules with assembly indices above 15 would be evidence that selection had occurred somewhere in its history. An exoplanet atmosphere containing such molecules would indicate that something was driving the accumulation of complexity against the thermodynamic tendency towards simpler structures. The framework was, in principle, deployable on samples from Enceladus's plumes, from Titan's organic surface chemistry, from the atmospheric spectra of distant sub-Neptunes, without requiring researchers to decide in advance what form life should take. The complication was one that Cronin and Walker acknowledged directly. The framework dissolved the boundary between biology and technology. A computer chip and a living cell both scored high on the assembly index. Both were products of selection, of processes that accumulated specific complexity against random degradation. The search for life and the search for technological civilizations, which the field had treated as distinct enterprises conducted by separate research communities, became, under assembly theory, a single question about any process that created and maintained molecular complexity above the threshold. This made the framework more powerful and simultaneously more philosophically demanding, because it required abandoning the intuition that biology and technology were fundamentally different phenomena rather than two expressions of the same underlying physical principle. Sarah Walker's contribution to assembly theory represented one axis of a broader reconceptualization she had been developing across multiple research threads. The assembly index gave a measurable, chemistry-independent signal for selection. Walker's parallel work on information theory gave a different and complementary framework, a definition of life as a type of physical process rather than a type of molecule or a list of properties. The definition came from asking what living systems did that non-living systems could not, and the answer she arrived at was specific. Living systems propagate causal information against noise. They maintain internal patterns that thermodynamics alone would dissolve, not simply by adding energy from outside to compensate, which any refrigerator does, but by using information encoded in their own structure to direct the energy flowing through them. A crystal growing in solution is an example of pattern formation, but the pattern is imposed by the crystal's external environment, by the geometry of bonding angles the molecule's chemistry requires. Remove the solution or change its composition and the crystal stops growing. The pattern has no capacity to maintain or replicate itself against disruption. A living cell grows, maintains, and replicates its pattern using instructions encoded in its own structure. The cell does not simply respond to its environment. It acts on its environment in ways directed by its internal information. This difference between externally imposed pattern and internally generated, self-maintained information flow was what Walker identified as the signature property of life, and it applied at every scale from a single bacterium to a planetary biosphere to a civilization. The consequence for the search was significant and had not been fully worked through. Under this framework, the distinction between a biosphere and a technological civilization was one of information storage medium, not fundamental process. Both were systems maintaining and propagating complex causal structures against thermodynamic dissolution. Both resisted entropy through information. The question of whether a planet harbored life or technology collapsed into a single question about whether its chemistry showed signatures of selection, information propagation, and self-maintenance against noise. The instruments designed to detect one should, with appropriate retuning, detect the other. Walker and Cronin's combined framework implied something uncomfortable about the search as conducted. The field had been asking whether life was present in environments it understood well enough to define life. It had not been asking what signatures of self-maintaining information propagation looked like in environments it did not understand at all. Every search for biosignatures was calibrated for the biochemistry that generated them on Earth, the only example available. A system propagating information against entropy through silicon chemistry, or through sulfuric acid reactions, or through energetic flows with no terrestrial analog, would produce no signal any existing instrument was designed to recognize. The search had found nothing that matched what it was calibrated to detect. Whether that was the same as finding nothing at all was the question the next generation of instruments and frameworks was being built to answer. In the spring of 1959, Philip Morrison and Giuseppe Cocconi published a paper in Nature proposing that civilizations might communicate by radio at the hydrogen line frequency. Their paper was serious, careful, and well-reasoned. It was also, in a way that took 60 years to fully articulate, the founding document of a search organized around the wrong question. Morrison and Cocconi asked where to listen for transmissions from other civilizations. The answer they gave, the hydrogen line, made physical sense. The question they asked had already embedded an assumption that would shape every subsequent search, that the thing worth looking for was a transmission, that whatever was out there would be broadcasting, and that what it was broadcasting was something a 1959 radio telescope could receive. The assumption did not come from evidence. It came from who we were. The most technically capable civilization at the time of Morrison and Cocconi's paper communicated by radio. So the search was built around radio. When Frank Drake wrote out the equations factors to quantify how many civilizations might be detectable, the last factor, the one that proved most intractable, was how long a civilization remained in the state of broadcasting detectable radio signals. That factor assumed the state was temporary. It turned out to be temporary for a reason Drake had not fully imagined. Civilizations did not broadcast radio forever because they moved on to better technologies, not only because they died. The search had been measuring the duration of a technological adolescence. The corrections that had accumulated over 65 years all pointed in the same direction. Hydrothermal vent ecosystems showed that life did not require stellar energy. Ocean worlds showed it did not require habitable zones. Extremophiles showed it did not require mild conditions. Alternative biochemistries showed it did not require carbon and water. Rogue planets showed it did not require a star at all. Assembly theory showed the question of what life was could be rephrased into a question about molecular complexity that assumed nothing about chemistry. Walker's information framework showed the question of whether something was alive was a question about the relationship between internal information and thermodynamic entropy. Each correction dismantled one layer of the original assumption, and what remained underneath was a question nobody had started with. What process are we actually looking for, and how does it leave detectable signatures regardless of its chemical substrate? The field had not failed through incompetence or bad faith. It had done what science always does, begin with the example at hand and build outward from there. The example at hand was a planet with liquid water, carbon chemistry, and a star providing steady energy across a narrow habitable band. The search built around that example had been thorough, technically demanding, and scientifically productive. It had found 5,000 planets where before it had found none. It had characterized dozens of atmospheres. It had detected carbon molecules in the atmosphere of a world 124 light-years away. None of that work was wrong. The question governing what it was looking for was wrong, built from a sample size of 1, tuned to a specific chemistry, calibrated for a specific detection method, organized around assumptions that were contingent rather than necessary. The universe had declined to cooperate, and the universe's failure to cooperate was, at this stage of the search's history, the most informative result it had produced. Something needed to change at the level of the question itself, and change was, slowly and with great difficulty, beginning. In 2029, the European Space Agency plans to launch a spacecraft called the Atmospheric Remote Sensing Infrared Exoplanet Large Survey Mission. Its design goal is to measure the atmospheric composition of 1,000 known exoplanets across a broad range of sizes, temperatures, and stellar environments, building for the first time a statistical picture of what chemistry the universe actually places in planetary atmospheres rather than what Earth's chemistry suggested it would. 1,000 atmospheres mapped systematically, assembled into a catalogue that could reveal which chemical conditions were common, which were rare, and which were so far outside any known abiotic range that they demanded explanation. The mission was designed to understand the context in which the question of life could eventually be answered correctly, and the distinction between that goal and finding life directly mattered enormously. The Europa Clipper, launched in October 2024, will begin its sequence of close flybys of Jupiter's ocean moon in 2030. Over 49 approaches, its instruments will characterize the ice shell's thickness, map the chemistry of the ocean below through material that cycling ice brings to the surface, and search for plume activity that might offer direct access to ocean water the way Cassini found access at Enceladus. The Dragonfly rotorcraft is scheduled to reach Titan in 2034, carrying instruments to examine the organic chemistry of a world that runs on liquid methane and nitrogen, searching for the complexity that would mark chemistry advancing toward the conditions from which life might emerge. Each of these missions was built under the scientific culture that preceded the full correction. Their instruments were selected before assembly theory, before Walker's information framework, before the implications of quantum biology had been absorbed into mission planning. They would produce important science. Some of them might find life. But the more significant shift was conceptual, and the conceptual shift was ongoing in research groups across a dozen institutions, in the margins of papers on molecular assembly indices and information propagation and biosignature philosophy. The original question Frank Drake asked in 1960 was whether there was anyone out there transmitting. The question carried inside it a portrait of who the answer should look like, a civilization that knew the hydrogen line, that had radio technology, that had decided to announce itself, that was close enough and powerful enough to be heard. The question was a mirror held up to one specific moment in the history of one specific civilization on one specific planet, and the search built around it spent 65 years listening for its own reflection. The question the next generation of searchers was learning to ask was different. What processes in the universe produce and maintain complexity against dissolution? Where does selection occur? Where does information resist entropy? Where does chemistry accumulate into structures that direct their own future states rather than simply responding to thermodynamic pressures around them? These questions carried no assumption about carbon, no assumption about water, no assumption about radio waves or oxygen atmospheres, or the distances at which habitable zones are calculated. They were asking what life was as a physical process, rather than where life existed as a confirmed fact. We had not been asking the wrong question because we were incurious or careless. We had been asking the wrong question because the right question was harder, because it required giving up the certainty of Earth as the reference, because it demanded looking for something we had not seen rather than something we already knew. The universe has been performing chemistry for 13.5 billion years in conditions we have only begun to catalogue. We have studied one example from the inside for the duration of a civilization that is, on any cosmic scale, less than an eye blink old. And we are only now, at the beginning of the third decade of the 21st century, learning to ask not whether something out there looks like us, but whether something out there is alive in a way we have never imagined, waiting to be found by a question we are only just now learning how to ask.